So the design is similar in format the way we discussed URL shortener. The same template we are going to follow. We will gather the requirements, and then from that on we will design the further system. And as I told that in your mind, keep this template in your mind that you need to gather the requirements two ways. First is functional requirement, meaning what your application is supposed to do, and another things are non-functional requirement, that what kind of availability it can have, and what are the compromises it which is allowed in this context. Probably some applications will be high on security, that also will come under non-functional requirements. So anything which is not related to the exact functionality of the application goes into the non-functional requirements. So keep this template in your mind. You don't have to say it out loud that you are collecting functional requirement or non-functional requirements, but it gives you a good framework to ask questions. Is that all right? Any doubts till now? Well, I'll assume no. Some of you might have attended the last session, so you might be familiar with this template. So capacity estimation, just like we did it last time in URL shortener, we will assume some number of users. We will assume how much data it is going into our system, how much data it is coming out of our system, and based on that, we will put a ballpark figure of how much capacity we need to maintain from the point of view of storage, from the point of view of bandwidth needed, and from the point of view of the capacity of the applications or number of servers, all sort of things we will figure out from that. So I'll start from the beginning. I have assumed a rough number of users like 1 billion users. Yeah, it seems your application is pretty famous and so many people are using it, and there are total 1 billion users, but all 1 billion users are not logging in daily on consistent basis. So on an average, you can assume 200 million users which are logging consistently on daily basis. We also call these users as daily active users. Some people also call it as DAU. It's a famous term in the business circles. And what these 200 million people do, now I am going to assume next thing that they are putting out 100 million new tweets per day. So 200 million people are logging in, and 100 million tweets are put on an average per day. And every user follows 20 accounts on an average. That's a gross assumption, but somewhere we had to start, right? With lack of data, you have to assume something, right? It might not be 20, it might be 50, it might be 100 or 2000, whatever, but you have to put a baseline and average figure so that it becomes easy for the calculations further on. Now we have assumed these three things. Now further assumptions are what does average user do? Average user, let's say, opens Twitter twice, and in one go it scrolls the feed and it sees and that user sees 100 tweets each time, and every fifth tweet has an image and every 10th tweet has a video, right? Each character has 2 bytes, which is pretty standard, and with metadata about 30 bytes for each tweet. Metadata in the sense that it might not be directly visible to you in the tweet itself, but all the information which is which is related to it. For example, the creation time, or if you want to tag someone, all sort of information which might not be visible in the tweet itself, but in the background they help to manage your tweets and save it in better way. We'll see later on what it means. I'm hoping everyone is fine with the capacity assumptions. Is there anything else someone wants to add over here which I might have missed? because assumptions can be different for different people, right? Some people will assume differently, think of something which I might have missed out, and some people will probably make a more exhaustive assumptions. So it depends on person to person, and this is my way of doing things. But let's move on. So here are some calculations based on previous assumptions. I've also assumed that 5 favorites are done per user. So 200 million daily users, and they have favorited 5 tweets per day. Comes around 1 billion. Now, how much total views per day? That comes around 200 million into 100 view per person. As I told right in the previous slide, that each person opens Twitter twice and sees 100 tweets each time. So 100 million tweet, 200 million users, 100 tweet view per person. Well, it should have been 200. But as I told that each user opens twice and sees 100 tweets per day, right? So it should have been 200, but it's okay. Ignore that small mistake. It turns out 20 billion per day. That's the total number of views for tweets. Let's estimate storage now. So based on this above assumptions and estimation, the total storage for 100 million tweets per day will be 280 characters. That's the upper limit for each tweet. If you guys don't know, you can't write a tweet of more than 280 characters. Earlier it was 140, now it is 280. So 280 characters, each character takes 2 bytes. So this is the total number of bytes for your text and 30 bytes for your related metadata. And calculation comes around 59 GB per day. And now we also assume that every fifth image is going to be, every fifth tweet is going to have an image. So I have divided 100 million tweets by 5 to get the number of tweets with image, and estimated that probably one image could be of 200 KB. So it turns out we are uploading 4 TB per day amount of images. Similar calculation for the video. Every 10th tweet is video, so it comes out 20 TB per day. Now we sum everything all together, then it comes out 24 TB per day data is being generated in your application. And as I told in the um, previous discussion, that we generally assume that our application will stand for at least 5 years. So we multiplied it with 5 and came around 43.8 petabyte of storage. So that's the amount of storage you need at this point of time when you have these many users. So um, I have done this calculation like beforehand just to avoid the calculation on the spot and wastage of time. But if it might have some mistakes, but that's not the point. I'm not trying to demonstrate my maths. I'm trying to demonstrate how to do the calculation. And if you guys find out any mistake, anyway, point out. Okay, so this is storage. Similarly, we can estimate for how much bandwidth we need, bandwidth per second. So the total reads happening. 20 billion reads are happening here. So 20 billion reads are happening, and 560 bytes are being read for the text. This is image, this is video. So we are reading around 2211 terabytes per day, which comes out around 25 GB per second. So that's the amount of capacity your system should be able to withstand. That's not a small amount, by the way. And the total writes comes around 60 GB per second, similar with a similar calculation, right? And yes, one important thing to note is here we have calculated per second here on an average basis. We have assumed that every second of the day will have constant amount of traffic, but in reality that never happens. During the day there are a few hours where your traffic will be peak, and some hours will have like traffic null. For example, in the night traffic will drop down significantly, and probably in the afternoon and evening it will it will spike hugely. Why? Because so many people are coming from work or school and logging into their accounts and seeing what's going on, and that's how it gets a spike. And to estimate the spike, I keep a general rule of 20/80, that 80% of the traffic is going to happen in 20% of the hours. Okay, so that's a general rule you apply when you want to estimate such kind of things, because 80/20 rule says that only 20% of the things which are important and 80% of things do not contribute as much, and we can take out the similar analogy here and apply the same logic. I have appended this note just in case you get a cross question from the interviewer that what happens around this scenario, and so it's a good thing to point out beforehand. It will give you extra points, so and it will show that you have considered all these things beforehand, and probably you have worked in such systems in previous jobs or previous projects. So it will give you a good edge points. Just point it out whenever you estimate. All good here? Okay, I'll assume all good. We'll go to the next slide. Now let's design the APIs. So for the sake of simplicity, I have given you only two APIs, one for update, one for retrieval, basically one read, one write. We have other APIs too, but we won't get into those. If you want to really dig into the real Twitter APIs, which Twitter itself has developed, you can go to this link and see what what APIs are there. I will not spend so much time over here because it's a huge topic in itself and can be discussed at length later at some point of time. But uh, the you get the point, right? Here in the update UI, it's a post HTTP request. Status is one of the parameters, and rest of the data goes as part of the body with this post request. Does anyone like feel that I'm talking something weird here and not able to understand? If anyone feels like that, I will go further and explain it. Let me know. Anyone? Okay, so I will assume uh, you are understanding everything around APIs, right? You know REST APIs, you know POST, you know GET, you know HTTP and HTTP body, all sort of things. I'll assume you guys know, right? And if anyone feels like they don't know, just message me privately anytime, whenever you feel like there is some confusion, right? Let's go to the next. What about database design? So again, I will iterate a few points here. The database design I have done in again RDBMS fashion, where you have tables, you have columns, you have predefined schema, and you pretty much know beforehand. It need not be the case. You might opt for a NoSQL database where you don't need to uh, design your schema beforehand, and it will be easier for you. But as many people are already aware about RADDBMS and they might have worked with SQL queries, so it is easier representation for them. At least for simplicity sake, this is good for now. And we will discuss other alternates like NoSQL later on when we expand and scale our design. So we'll go into that. I'll quickly go over each table. So this is tweet table. You have tweet ID, you have user ID as foreign key, and tweet ID is primary key, and these are the details which you want to store for a particular tweet. And similarly, this is user table, user ID is the primary key, and these are the details which you want to store for one particular user. And now this is the follow table where you maintain the pair that who is following whom. If you want to retrieve my to my following list, then you can just query from this follow list like select star from follow where user ID is equal to something. And then again, if you want to save the favorites, then you need to store that who favorited what tweet, and you are similarly storing that data in this table. So let's go on to the next slide. So again, just like I told, just like our template in our previous system design discussion, you don't have to start with a complex system design. Just start small, just like you would do in your data structure questions, where you want to start with the brute force solution and then move on to complex solutions and efficient solutions. Same approach you can apply in system design. See, I have not done any smart thing over here. We have just one client assumption, we have just one server, we have one DB and one file storage. But one thing to note here, we have a separate file storage. We are not storing our media in the database itself. Why? First of all, is there a way to store media in the database or not? Are you guys aware of such thing? Anyone?
There is some feature called blob or something by which we can store media in MySQL. I'm not sure. I haven't used it, but heard something like that. Blob and
Yes, you're absolutely right. We can store it like blob. That's the correct terminology.
but is it good? Is it like efficient to use a blob or something, or is it good to have external database and store the media files over there and
So
then
as you have already seen that we have huge requirement of storage, right? And database won't help. If
right?
you do not have like that huge requirement, you have very small blobs, then it doesn't make sense to create a separate file storage. But in that case also, I would personally create a separate file storage system rather than putting everything in the database.
Mm-hmm.
Primarily, databases are generally cost you more if as compared to the file storage. And the good thing is everything is stored at one place. So it's a trade-off.
Right.
Uh, is my voice like audible to you guys?
Yes.
Just realized that it might not be great because I am using my laptop's audio, not the headphone ones. So if that is clear, then no need to worry about. We can continue.
Yeah, it is good.
Okay, perfect. Let's go further down and see what are the problems with this design in our system. So before I go to the next slide, can anyone start pointing out what are the probable problems for the kind of requirements we had in the first slide? I will need a couple of responses here, at least some guesses.
Single point of failure.
Perfect. Single point of failure. What else?
We are storing all the media files like videos and images in just S3 file storage. So if someone is putting making request from some other location, then it might take some time. So we might need to like make some arrangement by which it is available to different ACEs, available locations, and then
Correct.
like CDN or something.
Yes, perfect. So yeah, so these are the two important ones, and there are some minor ones we'll see in the next slide. As I told that your traffic, you have such a huge traffic that one server might not be enough. You have to put a lot of more servers, right? And then as you see, you have so much write happening on a single day, and if that is the case, then your write operation will hog on to so much of the system resources, then there won't be any space left for the read operation. So technically you might want to separate out read and write operations, right? Then there are many single point of failures. We don't have any redundancy. And then database scaling. What happens if your one database is not enough? What do you want to do? You will have multiple databases. There's a term for there's a term for it when you want to scale the database into the multiple databases. Does anyone want to guess what that term is? When we have so many databases, we want to distribute our data into multiple databases.
Sort of clustering and sharding, like sharding in which we make partitions, but clustering sort of in which we can make
Yes,
replicas of database sort of.
yes, correct. That called database clustering. So, and then there is a functional problem here. When you guys can imagine, when you open the Twitter, there's an infinite scroll feed, right? You keep scrolling, you keep scrolling. With the current database design, what is going to happen that every time you scroll and every time you scroll, every time you have to probably fetch, even if you want to batch the feed, still you have to fetch from this database function, and probably it will at some point, if so many people are using at some point of time, then this database is going to be the bottleneck, right? You have to probably join multiple tables and fetch the data, and as traffic grows, those joins will become costly, and someday the database is going to go bad, or at least it will create a lag in our application, which we don't want, because as part of requirements we already saw that we cannot accept the latency of less than 200 milliseconds. So that's gonna be the problem here. And how about handling huge media files in a better way? We'll see later what it means. How about celebrities? Suppose some celebrity has millions of followers, and what happens in that case? Whenever that celebrity tweets, now it is going to appear in so many people's feed, right? Technically millions, and probably your system is not well enough designed to handle such scenarios. So we'll see, and we'll see what solutions we are going to apply to handle such things. So there are some uh, off of the, like, your basic conventional things which you want to employ. For example, load balancer. If you want to increase the server, you want to put in a load balancer somewhere. You want to employ a CDN, right? There are media files, right? You want to store these media files spread over in all the geographies. For India, it could be Indian CDN server, and for US, it could be US CDN server, and they both would store the same media files. If you are accessing the media from the US server, then it will fetch from US's CDN server, and same with India or anything else. So this is a very good use case of CDN, where you want to distribute your media based on geography. Now then there is a fan out load and fan out write and hybrid technique. We'll see what it means in the later slide. I'll not go into detail now. And then again, I already told that we can probably want separate read and write servers, so that write doesn't interfere with the read operations. And as you guys can see that our application is anyway read heavy, so read are very important, and uh, write shouldn't ideally interfere. And then database sharding, as we have already discussed. So yeah.
For this database sharding, I was recently asked in an interview that what different techniques can be used for database sharding, and like how are you going to divide, like partition your database? What different techniques you use for making these partitions? So what can be the good answer for this?
So again, there are many techniques, and some technique might make sense in some of the scenarios, but it will depend on the type of the application. Uh, for example, first of all, sharding is the intelligent distribution of your database information into multiple databases.
Right.
Because one database is not enough. Let's say you have now 100 databases, and whenever a query comes, you don't want to scroll through all the 100 databases and find your information. You want some intelligent way to figure out that which database might be having this information which I'm trying to fetch. then it will directly go to that database. Now, to intelligently distribute that data in the database system, these techniques are called partitioning. Let's say,
So, okay.
go ahead.
So suppose like we designed a, marketplace sort of application in which we can view the items, place the order, and add the items to cart. And there was some admin page from which we can upload the details. So there were like four different tables for this. And so if I say that I had done this sharding on basis of this four different tables, that we had created four shards for four these different tables, then is it a good idea to say this, or would it be like it's not possible? Like,
Well, you have to think about what are the downsides of your this thing.
Totally.
Good idea. It's a good first start, but there are several downsides. Because let's
okay.
say some of the sellers, if you have divided based on the seller ID, some of the sellers might be huge, right?
Hmm.
So that cluster will become significantly larger than other clusters, and that cluster will probably serve 80% of the traffic, which you don't want, because of that that is the reason why you did the sharding, right?
Yes.
So that defies the purpose. So you want to upgrade to some intelligent method.
Okay, makes sense. Got it. Thank you.
Okay, let's move to the.
Amnish, hello.
Go ahead. Go ahead.
So basically, in the scenario that she said, in that if we need to join the tables, then we have to uh, get the data. Like join queries will be difficult, right? In that case,
No,
because they're all.
actually, in our case, what we had done, like we had made the internal API calls. So if any particular if we need any detail from any other database, any other table from the other shard, we'll make an internal API call to that shard, and that internal API, and like there was different internal APIs to handle this kind of request, I think. So we don't need to like perform any joins over here. In our case, it was like that.
Okay, got it. Okay.
Yeah.
Yeah, that is right.
As you guys can see, this is little bit more advanced design, which inculcates a lot many concepts, and we'll go step by step and figure out at each step that why we did what we did. Let's start from client. So here still it's a broad design, still so many nuances from this design are missed out, and I will try to catch up some of the nuances which are missing in this design. And if interviewer might push you for to explain some of these nuances later on, so it's a good thing to understand these things. So when I say clients, clients can be your mobile, clients can be your database, or clients can be as diverse uh, as TVs, Android TVs. You can access all these things from TVs, and all these clients will have their specific requirements, because your mobile might not need so much scroll at a time, so many tweets on your feed at a time, because there's a small screen and you can see as much only on small screen. But if you have logged in from your desktop, then you need so many tweets on your timeline, or your feed at the same time, right? And if the bigger client, then you need more bigger, right? Based on that need, you might want to push out that number of tweets at a time. So that might change a few things at this level. And then for mobile, the access mechanism might be different. From mobile, you might be passing it via some payment, for some API gateway kind of system. And if it's a browser, then you might want to hit the APIs directly to the server. But it depends on like client to client. I have missed out that detail over here just to simplify things and understand other important parts. So, as we have already figured out that CDN is a very good thing in this design, then I have put a CDN over here. In the background, this CDN will keep syncing with these read media storages, and every now and then it will keep updating. And again, as I told, that CDN is more like a cache dedicated to some media, heavy media files, and sometimes that cache might expire, and you have to replace it with the new one. And sometimes your CDN, some stuff doesn't make any sense, because if you assume that some movie is released, then you will see a surge of video, a demand for that video uh, in that particular time. But if that movie gets faded out after, for example, a year, don't want to store it. You don't want to delete it. Whenever any odd user comes and wants to access that video file, you just want to fetch it directly from the database, so just to save the cost, right? I'll move on further. Again, we have put in load balancer here just to route our queries for read and write based on intelligently, and distribute the traffic among servers. And again, as I have told, that I have separated out read and write servers here. All the write traffic is going to go here, read traffic is going to come here. And uh, whenever write happens, then it will directly go to the database and it will write, and then it will write the media to this DDM, write media storage. That's the wrong spelling. It shouldn't be read here. It should be just write media storage. Okay, so the write flow is pretty simple. But what happens whenever a new tweet is written? That's when the real magic happens. This write database pushes out all the information about that tweet to the read DB and read media storage over here. And these read storages are used to generate the feed. Now, here I want to touch upon the points when I said fan out on load and fan out on write. So, what is fan out? Uh, Fan out is just a fancy term of generating your feed or timeline on the go. So, that's called fan out. And fan out load and fan out write are two different techniques via which we want to create that timeline. Fan out load happens when a user is fan out load is implemented in such a way that when a client refreshes its browser or app, then all the stuff, new stuff gets pushed to its timeline. Until unless the client or user doesn't refresh, nothing will happen. It is dependent on the client. So the downsides in fan out load are that there might be so many empty refreshes, right? So many times user might refresh and you won't have any data, but you will still end up querying your infrastructure just to fetch some information, right? There are techniques to get over with it. I have not written out all those here, but from some of these techniques, I'll just cite it out. You might want to research it further later on. Some of the techniques in the front end side, uh, we have called e-tag libraries, or even you can use cookies to figure out if anything changed on the backend for that system. And without going to the backend infrastructure, the moment you hit your server, you will immediately know that nothing changed for this person, and let's move on from here. You won't have to go to the backend database. Again, this is very simplistic explanation. It might not be that simple. There will be edge cases which you might want to handle differently, but I'm just saying it out loud here. uh, Another problem is that it is dependent on users refresh, and it might not be a great user experience, that you might be showing the stale data on users timeline if the user doesn't refresh. To handle that, you might implement the forced refresh every now and then, but then again it will create a problem in your front end. It might create a problem in your front end. It might not be that simple. So as I'm telling that every problem has a probable solutions, and all solutions have some upside and some downside. And while designing a system, you have to seriously consider that for your current problem, is that solution the right one? The downsides of the current solution are consumable, are okay, for the system you are designing, and based on that you will pick the solutions. So as I have already told previously, there is no right solution in all the circumstances. Someday you have to compromise on something, and other day you have to compromise on the other thing. That's how system design is. So I hope you guys are clear on what fan out load strategy is. Is there any questions regarding fan out or fan out strategies till now? Okay, I'll assume no. I'll explain what fan out right is. As you can see, uh, fan out right is opposite of the load. The user doesn't have to load every time. The timeline is generated whenever a new tweet comes which is relevant for the user. So let's say there are hundreds of people who are following me, and if I tweet something, then all these 100 people will be notified on that right. So that is the right. That's the opposite way of doing things the way we were doing as compared to the way we were doing in an outload strategy. So then, how it is implemented? We could use some kind of technology of long pole. Uh, well, long pole is a strategy where you keep polling a remote resource and checking whether something new got generated or not. And whenever something new gets generated, you pull that, but you constantly keep polling that. And why it is called long poll? Because that poll is not not a small one. You poll to the resource and you wait for a long time and nothing happens, then stop. Again, you poll, wait for a long time, keep establishing that connection, and then stop. The downside is for this fan out right approach, there will be so many connections which will be occupied for the long poll, and then there is a potential problem of celebrity user. Let's say celebrity has 25 million followers. Whenever celebrity tweets, then you going to push to all those 24 25 million users at a time? It will break your system. You don't want to do that. So that's the downside of fan out right strategy. So the good solution, as in real life, is always hybrid for both of them. When you want to create a hybrid strategy, then for normal users, it might make sense to make uh, make do with fan out right strategy. If I have only 100 followers, then I wouldn't mind to push out my tweets to all those 100 followers. But if it's a celebrity, then you don't want to push it. You want to push out fan out loud. So whenever user refreshes, then only the tweet for that celebrity gets pulled. Otherwise, by default, it doesn't get pulled. And we can get away with all these things because you don't want to be instantly notified whenever a new tweet comes. Right? If I have tweeted and if you have seen my tweet probably after 1 hour, it will be still okay. It is not a instant thing, just like messaging. When you message someone and you want an instant reply, that's not the thing. We can have some kind of latency between the tweet generation of tweet and read of tweet. So those kind of trade-offs we can do here, right? And then there is another strategy which you can use, and I think in my opinion this is the best till now, and I would employ that whenever I design a system. That's called pull to push. Whenever a tweet happens, irrespective of the who is tweeting, you do not push out the whole payload of the tweet to the end users. You just notify end users that, hey, something new got generated, you might want to be interested, you might be interested in that. And that uh, that is notification asking that go ahead and refresh it. So that's called push to pull. In first step, we pushed our end user to pull the data which has been generated. And whenever that user pulls or refreshes, then we actually send the actual information. So it saves a lot of resource because not many people will be online at that instant, and all those people who are online, only those people will be refreshing, and you have saved so much on the resource. And again, you guys might come up with the new creative solutions, that how do you want to employ all these strategies and technologies in even more intelligent way, so that you can design an efficient system. And feel free to think out and discuss with your friends that what would you do in such scenarios and what are the downsides of those new solutions. I'll encourage everyone to talk among friends and figure out. And then the last piece of the feed which I want to discuss is feed ranking. So if you have seen in your Twitter or Facebook that your feed is not chronologically generated, feed is generated on based on your history of data. If you have posted about India a lot of time, then you are more likely to get the all those status which have India in their content than any other country. So you want to rank the feed intelligently. The most basic solution is of course chronological order, that is based on time. The latest tweet comes first and the oldest tweet comes last in your timeline. But that is not very good technique to use, mainly because you might not be interested in all of the tweets, and other mainly because it will destroy your infrastructure in lot severe way than in any other case. So when you feed rank based on some intelligent technique, then you will be able to reduce your infrastructure cost a lot, and without compromising uh, on your service, because you are showing what someone wants to see, and you are not showing what someone doesn't want to see. And of course you want to do that intelligent calculation before taking such a call, and that's when you want to employ machine learning techniques and all sort of things which intelligently figure out on the go whether this content will be relevant for a particular user or not. All right, so we discussed four things here. First, fan out load, fan out write, hybrid, and feed ranking. Any confusions or doubts in these things? Okay, I'll assume no. So we'll move forward. Now you understand all those concepts. Let's discuss how the feed is going to get generated. So we were assuming a scenario where a new tweet or content was generated, and we flushed out that data into our read replicas. Once read replicas have the data, then this is feed generation service, which will uh, create a offline feed beforehand. Yeah, one important thing actually I forgot to discuss, that whenever you open your Twitter application, your feed might not be generated on the go. Like the moment you open the tweet, that's when you query so many servers and databases, and you generate your tweet. So to reduce down the cost, you want to pre-create all the timeline for a particular user in your cache somewhere, and whenever that user logs in, you access the data from the cache rather than going ahead and pulling all the information from your database at that moment. Why? As I already told that uh, when you want to fetch at that moment, it might be very time taking, because based on our database design, there might be so many joins getting involved in collecting all the data. And if there are so many users are involved, and there are so many users who have so many followers are involved at the same time, then it will create a problem in your database, and you won't be able to fetch that data in a timely fashion, and you will definitely face some lag in your application. So to do away with all that, we use cache, and we pre-create the timeline and keep that stored in our cache. And whenever that user logs in, we hand over that pre-created timeline to the user. But what's the downside of it? Are you guys going like having any thoughts around it, that how much data or how far we want to generate the timeline beforehand? You definitely don't want to generate from start to the end of the timeline, from the beginning of the time when user got created and till now. You don't want to create that timeline. Is there any intelligent way to figure out that how long you should pre-create the timeline before you actually have to query your backend to get the further timeline?
Is it
Any
a good
ideas?
idea to like have some cron jobs, which is like scheduled for like every 1 second or something? This service should get called and generate a timeline for, and then like something like that, some cron job service like that, which is scheduled at some specific time of interval.
Yep. So you can do it with cron job, but cron job will be like little raw way of doing it. You don't want to depend so much on the cron job for this functionality. You will have a dedicated service written, dedicated feed generation servers for that. And whenever a new read happens, at that moment you want to append the newest tweet in all those people's timelines for those that tweet is relevant,
Right,
right? So because you want to and this feed generation service, let's assume it's chronological order for now for the sake of simplicity, and you want to surface the latest tweet first and older tweets later. So whenever a new tweet comes, you want to append that tweet to the start of the timeline for each user, right, who is
but
interested in that.
is it easy to track the changes in database? Like there are millions of new tweets coming on in Twitter, right? Every
Hmm.
second.
Hmm.
So is it easy to track those things? Like if interviewer asks you that, how are you going to track those changes or track new tweets to append to the our service? Like then how are we
Hmm.
gonna track that?
Yeah. So very good question. So again, I have missed out uh, more detail here in the service. Generally, that happens using uh, technologies like Kafka or SQS, Amazon SQS. So these guys are messaging infrastructure. You can imagine these infrastructure as a long and broad pipe, and whenever a new tweet gets written into the database will immediately put that message into those messaging infrastructure technology. And this feed generation service might be listening to those topics in the messaging service messaging. Let's assume SQS for now. Feed generation service will be listening to those SQS, those topics in the SQS, and whenever the new message comes, they get fed to the feed service. Now there will be influx of huge amount of tweets into the messaging infrastructure, right? So that's where messaging is useful. You can dump a lot of messages into the message into the SQS kind of thing, and where it will uh, it will store everything temporarily, and at the other end it will some user might be pulling out all the messages, and as long as there is data in the SQS message, the feed will keep pulling it. You can again partition those SQS based on so many parameters so that you just don't have one SQS to have all the messages in one place. And that's where you can distribute those messages, and feed might be listening to them based on different topics.
Okay, this makes sense. Thank you.
Any more doubts? Okay, let's go ahead. So till now we have pre-created some feed generation service, and yeah, the question I was asking that how will you determine how much feed you want to create? Because any user's feed might go to millions of tweets, but you don't want to store all those millions of tweets in this cache. So we can use simple strategies like the latest 500 tweets for the timeline are stored in cache, and if user wants to scroll beyond 500 tweets, then he has to go back to the database and fetch the information from there. And then you can use some intelligent techniques. uh, for example, if user opens the tweet once in every month Twitter once in every month, then you don't even want to store in the cache. For once in a month user, you just want to fetch from the database and don't want to spend your cache for that, because caches are costly. And if the user is logging every day twice, then you might want to store based on his consumption of the Twitter service. Based on that, you might want to calculate on the go that this user might be scrolling 1,000 tweets per session, and based on that you might want to store. So as I'm saying that, again, you might want to employ some machine learning technique based on the history, login history, and usage pattern of the user, and based on that you can take a call on person to person basis that how many tweets you want to pre-create and keep in the cache. Does that make sense?
Yes.
Yeah. So, and once you have pre-created tweet, your whenever a read comes, then load balancer redirects traffic to your read servers, and read servers go ahead and fetch it from cache. If not, then we go all the way to the database and bring down. And whenever we fetch from the database, then while coming back uh, we will write to the cache also that data whatever we have just pulled, just in case it is being used again in in in, uh, in the next few hours or next few days, just to keep the latest data in the cache, and then serve the traffic to the client. Okay, so this is more or less discussion for the advanced design. Now I want to move on to other things like why and in which cases actually NoSQL makes sense rather than putting everything in your RDBMS. Or when I say NoSQL, in this case I am trying to say any key value pair kind of data space. Amazon Dynamo is very good example, and probably Redis is also one of the key value pair. I'm not sure about Redis. I haven't used. So imagine a situation that you have need, as you will have often in this case, you have need to fetch all the people who are following user A. One way is to query the database and your table and fetch those. That if you go back to the database design, yeah, you can query this table. But as you can imagine, this database table will blow up after a point of time, because for if I have 100 followers or I follow 100 people, then there will be 100 pairs for me alone stored in that. And if each user follows 100 people, then for each user there will be 100 rows generated in your table. And this is exponential growth, and it will like go blast. In that case, you don't might not want to store all the information in this follow table. You might want to store it in NoSQL key value pair. Key will be user A, and value will be all the IDs of the users who follow user A. So whenever user A tweets, you fetch all the people who are following user A from this NoSQL key value pair and uh, insert that tweet in those people's timeline. So you didn't have to query the whole RDBMS database based on that. Similarly, you want to store the timeline also in NoSQL. If you have decided you want to store the latest 500 tweets, then you for user A as a key, you can have another equivalent of table in the NoSQL where your timeline is created here. And whenever a new tweet comes, all you have to do is insert that tweet to the front of this timeline in the NoSQL database. For this case, also NoSQL makes sense. Okay. So we have covered a lot of ground here and we have discussed so many techniques. And as you can see that our URL shortening service was far easier as compared to the Twitter creation. And your interviewer might want to focus on any one particular case here. Let's say you uh, went all the way down and you created this design. Now for follow-up questions, your interviewer, based on the type of company you are interviewing with, and based on the expertise of the interviewer, he might want to grill on some of the specific topics. Let's say you are going to Facebook. If Facebook asks this question, then they will be grilling on the graph information. How will you store that who is friends with whom, and what that data storage look like? And if you are going to some company which is database heavy like Oracle, they might want to grill on the database side, right? And for Netflix, they might grill you on the CDN side. And in general, anyone can grill you on the API side. That what kind of APIs you are going to create, what will be put, what will be get API, how your payload would look like, and all the related things. And based on that, you have to like go down the path. But as I always suggest, try to drive your interview rather than give the control to the interviewer beforehand. Try to do it slightly in a non-explicit way, but if it happens that you are not able to do it in very non-explicit way, just tell upfront that this is your area of expertise and you want to tell more details in this area, not in any other area, and your interviewer will happily comply with that. But do that only if like situation is very very bad and you don't know nothing about everything else. Okay, let's move on to the next slide. And as you can see, we have missed down on so many things in the Twitter design, and still we ended up in such a complex design. We have missed out, and if what happens when someone wants to search, what happens if we want to employ messaging in our application, or how the tagging works, how do you tag hashtags, and how notification works. Whenever you are subscribing to some user, then you get notified whenever that user tweets. What are the follow suggestions? You have followed someone, you want to follow the similar user. As of now, Twitter suggests you already that these are the similar users you might want to follow. And what about the reply of tweets? What about the hierarchy of the reply of tweets? It gets way more complex than you can imagine, and if you include any one of these features, then your design will become completely different and will become more complex. So it is useful to take into consideration all these things and think through all these problems. And for sure 1 or 2 hours is not enough to discuss all these things. And I will suggest that treat this session as your starting point and keep drilling down the details for each of the functionalities. And there's so much material on the internet which you can find regarding any technology functionalities. And the companies themselves publish their engineering blogs, that how they have implemented such, how they have handled so much traffic. Similarly, there is a engineering blog for Twitter. It's a very good read. Just go ahead and access their blogs, and you will get to see that uh, what all things they are doing on inside to manage such a complex application. And then there are so many videos and websites which will explain all these things in detail. So I'll wrap up this discussion. If you have guys any doubt till now, you can ask.
Avnish,
Hmm.
for Twitter specifically, um, what database is good? Like, we don't really need the consistent data over here, right?
Yeah.
So we can use any of the NoSQL database according to CAP theorem, like MongoDB or Redis or any other NoSQL database. So
Yes.
is it like more better to use that one over here, or like RDBMS is a better choice, like for this Twitter specifically?
Well, in real world, you will never get to a company where you are not using uh, RDBMS or not using NoSQL. Almost always they will be using both. So NoSQL makes sense in some of the scenarios I have explained, right? And
Hmm.
for some of the scenarios, it might not make sense. And for consistency purposes, RDBMS is the best. That you
Yes,
might not be directly fetching the data from your RDBMS, but your source of truth would be the RDBMS when push comes to the shove. You will be pulling all the data from the RDBMS and putting it out into more readable and scalable infrastructure of NoSQL. And based on that, you will run your application. But still, you want to store the information in the RDBMS at the
RDB,
back of it.
right. Okay, got it.
Any more doubts?
I have one doubt, but it is out of this. Um,
Go ahead. We have 3 more minutes. You can quickly ask.
Suppose we are designing Book My Show sort of application. In
Hmm.
that, there is a requirement that if one user selects one site, then 10 minutes should be allotted to that particular user. And in that meantime, in that 10 minutes, no other user can get that site because that is blocked.
Hmm.
So, how do we maintain like this sort of requirement?
Okay, this is a long discussion, but this the combination of few techniques can help you in that. First is obvious. Our databases already come up with a locking mechanism, right? Whenever you want to write to some ID,
Mhm.
database locks that row and writes to it, and does it make sure that no one is writing to that row at the same time, right? So that is at very lower level. At upper level, you can employ techniques like uh, if you have heard about what do you call op- optimistic concurrency kind of techniques.
Okay.
Yeah. So first you lock that row, and uh, you populate your database with that information, and then you start writing it out. And if that user comes back in another let's say 10 minutes, then you write further information, and until that uh, you don't do it. And if that user doesn't come back in let's say 10 minutes, then you can let that lock go away.
Okay.
Again, I I have to read and study that how exactly these systems are implemented, but I'm sure
Mhm.
they are implemented in this fashion.
Okay.
Our session is about to get over, so I'll stop here. Well, thank you guys for coming, and I will posting this video soon on the YouTube channel. Thank you guys.
Thank you.
Thank you.
See you
Thank you,
next
Anish.
Sunday.